Okay, 8.5 is all about quadratic functions and parabolas. So hopefully these are not all brand new topics to you, but maybe they are a new way of looking at a specific formula, or maybe it is a brand new topic and you never really dealt with quadratic functions before, and that's okay. A quadratic function will always look like this. The f of x equals ax squared plus bx plus c, where a, b, and c are elements of the real numbers, and a cannot be 0. If a is 0, what happens is we lose our x squared term, and the x squared term is what makes it a quadratic function. So if you see something that has an x squared in it, and there's no other, like x to the third or anything like that, you're dealing with a quadratic. This is a very generalized picture of a quadratic function. This is the basic or the mother function for the quadratic, as we would call it. This is f of x equals x squared. There's no translations on it. It's not turned upside down. It's not stretched. It's not moved in any way, shape, or form. This is the basic function that we will always start with when it comes to graphing our function. And so what we have is we have this U shape, which is called a parabola. Just a special math name for this shape. It looks like a U. And it is symmetric. You'll see that this right-hand side is exactly the same as the left-hand side. And so since it is symmetric, we have an axis of symmetry that runs through what we call the vertex. The vertex, if you have an upward-shaped U, like we have here in this picture, will always be the lowest point. It's in the middle, and it's the lowest point on the graph. If our graph was shaped the other way, where it was a U facing down, our vertex would be the highest point on our graph. So quadratic graphs are parabolas. That just means it's shaped like a U. If the A in our equation is greater than 0, so it's positive, whatever it may be, then our U or our parabola will open upwards. And that's a really nice thing to be able to note straight off the bat. If your A is negative, so less than 0, then your parabola will open down. When it comes to graphing these, which we're going to do a lot of today, these are the first things I always look for. Which way is my U going? Is it up or down? If the A is greater than 0, so again, if we have a positive A, the vertex is known as a relative minimum. Again, that's just stating that the vertex is the lowest point on that graph. If you have a parabola that opens down, so that A is less than 0, then your vertex is called a relative maximum because it's at the tippy top of your graph. It's at the top of the U. The vertex, we usually label that with an HK, and you're like, well, where did that come from? HK is just another differentiator instead of saying X and Y, because when we look at our graphs and we have equations, they already have X's and Y's at play, and so we assign different letters so that we can keep it straight. The H value is the X value. The K value is the Y value. They're alphabetical, just the same way as X and Y. And we will see another format of our quadratic function, like the equation, where the H and K will show up, and it'll make a little bit more sense. And then your axis of symmetry is always whatever X equals H. Whatever your X value is at your vertex, that is where your axis of symmetry also lies. And an axis of symmetry, again, just means we can fold our graph on that dotted line, and the left side would lay right on top of the right side, and vice versa. So lots of good information. I definitely would recommend knowing that if your A is positive, it opens up. If your A is negative, it opens down. And having just a generalized picture of a U in your head whenever you see an X squared equation. Knowing some of these basic functions or mother functions will help you as you go to graph your equations throughout the semester. Especially today. We have to graph a lot of parabolas today. And that's okay. All right, I'm going to slide up a little bit. I'll try and leave the main graph up there. so that we have that to go off of. Probably won't get to, but I'll leave it up there for a minute or two. We're going to do some examples. We're going to graph two different versions of our x squared graph on here. It says graph the following g of x functions or h of x functions. But when we do this, we're also going to graph f of x equals the x squared on the graph just to simply compare. And so on Pearson, you won't do that. Most of the time, your graphs are multiple choice, and you just pick which one matches. But when it comes to paper and pencil, it helps us to actually visualize what has happened in our graph if we compare it to the original. And so a lot of times I will put the mother function on my graph just so I can see what kind of translations are happening. What does putting a negative in front of the x squared actually do to that graph? Or what does putting 1/2 in front of it do to the graph? And it's easier to see what happens if we have the basic mother function to compare it to. Are we okay if I keep scrolling up? Okay. Because we're going to have that same picture of the mother function here in just a second. Since I have to graph f of x equals x squared, I'm going to start with that one. Just graphing the mother function. The way you figure out where to plot points is you really just plug in x values and chug out problems, or chug out your y's. So when x is 0, if I plug it into my f of x function, 0 squared is 0. So you always start with your mother function at the origin, 0, 0. When x is 1, 1 squared is 1, so I'd be at 1, 1. When x is 2, 2 squared is 4, so I'd go up to 4. This is how we actually get the values to do our graphs. We're just plugging in x values and seeing what we get out. Now, as you get more comfortable and you start recognizing what a quadratic function looks like, then you don't have to necessarily plot all those points or have to do a table or anything like that because you'll know in general what it looks like. And I was able to fill in the left side of my graph without doing any number crunching because I know that my parabolas are symmetric about my axis of symmetry. And so if I move over 1 and up 1, that means I have to move over 1, up 1. If I move over 2, up 4, I move over 2, up 4. I can fold the left side right on top of my right side. That's how I'm able to come up with that. And then I'm going to label it just so that I don't forget that this is my starting point, this is my mother function. Now, the actual problem asks us to graph g of x equals negative x squared. So if you've had any type of a college algebra or algebra 2 class in the past, you might know something about the translations that occur within a function. I am not banking that you have had those classes, or if you have, you've probably slept since then. I know I certainly have. So the easiest way for you to graph these right now until you understand what's happening in them is to do a table. And when I say a table, what I mean is you will have an x column. You will have your, in this case, it's a g of x, like your function column, where you write out the equation exactly as it is. And then you will have a y, or you can call it an f of x column. And you will notice that even on our mother function, we did 1, 2, 3, 4, 5 points. And that is generally what I recommend as well whenever you are plotting any type of a graph. I always choose 2 negative values for my x's. I choose 0, and I choose 2 positives, which is actually what we did here. We did 2 negative x's, we did 0, and we did 2 positives. It gives us a pretty general picture of what's going on in our graph, and we can generally graph our picture from that. And so that's what I'm going to do. I'm going to let x be negative 2, negative 1, 0, 1, and 2. These points that I'm picking for my x's are completely arbitrary. That means you can pick completely different points, and we can still get the same graph. I will caution you that when you're picking your points, though, if you pick them really big, when you start squaring those, they get really big really fast. And I don't know about you, I don't want to do a whole bunch of tick marks. So we're going to see what happens, and then you'll be able to draw some conclusions on how this works without having to graph all the little points. Okay, so this one I specifically chose because this is a big thing that I harp on in Math 20, in Math 30, in my college algebra class, in this class, even in trig, I bring it up. There is a big, big difference between negative x squared, written like it is in our function, and negative x squared. These are not the same thing at all. And that aggravates people sometimes. But the exponent only applies to what's directly in front of it unless there's parentheses. So negative x squared, written the way that it is in our function, is the same thing as saying negative 1 times x squared. Down here, with our negative x inside the parentheses, we are saying negative x times negative x. And notice this will give us a positive x squared, where the top is going to stay a negative. These are different. These are super important to understand. I actually just taught on this yesterday in my Math 20 class because it's this important. Because here's what's going to happen. If you treat the negative x squared without the parentheses the same way, then all of your outputs up here are going to be wrong. And your graph's going to be wrong. So be careful about that. So here I'm going to write negative 1 times, and then in parentheses I'm going to write my x squared, whatever my x value is. That way I don't forget that I have this negative out here. Negative 2 squared is negative 2 times negative 2. That's a positive 4. But then we have this negative 1 outside, which gives us a negative 4.
Where'd you get the negative 1 from?
From the negative right out in front of the x squared. It's down here. Negative x squared with no parentheses is the same thing as negative 1 times x squared. And so I kept it split whenever I do this middle part of my table, just so I don't accidentally drop that negative somewhere. So I'm going to do that on all of these. Negative 1 times whatever my x value is squared. Negative 1 squared is 1, times the negative 1 is negative 1. Negative 1 times 0 squared, well, if you square 0, you get 0. 0 times negative 1 is what? 0.
Real quick, sorry.
Nope, you're good. Ask.
The negative 1 times negative 1 squared, wouldn't that be a positive or a negative?
So right here.
Yeah.
So this is negative 1 times negative 1. You have to remember order of operations. Exponents first. So right here, this would be positive because we have negative 1 times negative 1. But then we have to times it by negative 1 again, which gives us the negative. Here we have a positive 1 squared, which is positive 1, times the negative 1 is negative 1. Negative 1 times 2 squared. 2 squared is 4, times that is negative 4. Now I'm going to graph this on the same graph over here that I graphed our original one. At 0, I was at 0. At negative 1, I'm at negative 1. At positive 1, I'm at negative 1. At negative 2, I was at 4, so it's 2, 3, 4. And then I was down at negative 4 over here. Whoops, that's a g of x. So notice what happened with our graph by just sticking the negative in front of it. We did nothing else to the graph. Everything was exactly the same, except we put a negative out front of our x squared. That caused our graph to flip or to reflect over the x-axis. This always happens if you stick a negative out front like that. Always. I don't care what kind of graph you were originally starting with. If you're starting with something that looks like a W, if it's face upward and you stick a negative in front of it, it's going to flip it down every single time. So in the beginning, as we are graphing these and as we're getting more comfortable, this is probably the easiest way to figure out what those values are that you need to graph with. Are you required to do a table? No. Only if they ask you to fill in a table would you need to do a table. But it does help for you to generate out your Y's so you know what you're doing. Are there questions on this one before we see what happens when we stick a half in front? Okay. I'm going to rotate. And again, I'm going to go ahead and immediately put my f of x squared in there first, just so I have that as my starting points. So I remember what it is we're starting with, what it is that we are moving around and changing. So we got our vertex at 0, 0, then we got 1, 1, and we've got 2, 1, 2, 3, 4. We got our U shaped up, and this is f of x equals x squared. There's our basic mother function. So now for this one, we have h of x equals 1/2 x squared. And I'm going to approach it the exact same way we just did the last one. I'm going to make a table. I'm going to have an x column. I'm going to have an h of x equals 1/2 x squared. And then I'm going to have my y column. And again, I'm actually going to pick the exact same x values I did last time. Those are kind of my go-tos. They're the closest ones together. They usually result in quote-unquote nice numbers. They're small, so I don't have to change my graph to make it really big. So I'm going to do -2, -1, 0, 1, and 2. So when I plug that in, I will have 1/2 times -2 squared. So that's 1/2. -2 squared is 4. 1/2 of 4 is 2. And I'm going to do that for every single value as I move down. 1/2 times -1 squared. And once I've filled in my table, I have my 5 ordered pairs so that I can graph. And something interesting happened just simply by putting that 1/2 out front. I still have a 0, 0 in there. But notice what happened when I went from 1, now I'm at a 1/2. So I'm only going up half as high as I did previously. And when I'm at 2, I'm only going to 2 instead of to 4. Again, I'm only going half as high. So what happens is we kind of squished our graph. We actually squished it by a 1/2 because that's the number that was in front. Our leading coefficient for this quadratic was a 1/2, which means all of my y values got cut in half. So if that number out in front of my x squared would have been like 4, then I would have been taking all my y values and I would have been multiplying them by 4, and my graph would have grown upwards a lot faster. So it would have been a lot taller and a lot skinnier than the original function, which is why I like to put that original function on there, because if I just graph the purple function, which is the h of x function, I might not recognize exactly what happened. But when I put the original function right here next to it, I can see that what happened is it's growing at a slower rate. And so it's a fatter U, or a fatter parabola. It takes longer for it to grow up and out than the original green function. And that all has to do with this number that we put here. So if this number was a 4th, then it would be even fatter. If this number was 10, then it's going to shoot way up really, really fast. Now, do you have to memorize all of that information? Absolutely not, because you can always do a table. And what I always recommend doing is if you don't know how to graph something, make a table. Plug in some x's. See what happens with your y's. Yes, you should know that if it's an x squared function, then you should have a u. You should have a parabola. If you have a negative in front of your x squared, then it's going to be a downward facing u, because that's your a term. And if a's are negative, your parabola faces down. If your a is positive, then your parabola faces up. Are there questions? Yes?
The 1/2 and the negative are the A's?
Mm-hmm.
Okay.
Yep, there's just not all the other pieces necessarily so far. Because if we go up here and we look, our general form for our quadratic function is ax squared plus bx plus c. So whatever is in front of our x squared is our a term. And so for that first one, it's just a -1. So -1 is our a, which makes it negative. So we know it opens down, which is what we saw on the graph. Here, it's positive, so it still opens upward. It just made for a fatter graph. Other questions or clarifications, or what else you got before we move on? Because we're going to learn some other translations that happen. Okay, let me flip over. Vertical shifting and horizontal shifting. These I 100% would recommend learning. If you learn what these are doing, they save you a lot of table work. But again, if you forget, if you don't remember what these mean, make a table. Always make a table. But vertical shifts, if you'll notice here, we have our x squared term, regardless of which one we look at. We have our x squared term, and then we have plus a constant, so plus a number, or minus a number. If it's plus, we move our graph up by whatever that number is. So if it was x squared plus 2, we would take our regular mother function and just shift it up 2 units. That's it. If it's minus, we shift our graph down 2 units. So the vertical shifts are really nice because they happen outside of the square, so they don't happen to the x squared part. They're added on at the end, and they go in the direction you would logically think. Positives move up, negatives move down. Horizontal shifts happen inside of the x squared. You'll notice that we have x minus c in here, and then we have x plus c over here. These are inside of the squares. That's how you know it's a horizontal shift versus a vertical shift. Horizontal shifts happen inside, and they're going to move the opposite direction to what you think. So if it says x minus c, you're moving to the right that many units. If it's x plus c, you're moving to the left. And here's why that is. Over here, I went ahead and expanded it so you can see that it always is x minus something. If your c has a positive value, you move it to the right. If c is negative, you move it to the left. But you'll never see it broken apart like this. But it does actually logically make sense. It's just the formatting is weird. So I usually just tell students that for horizontal shifts, you're going to move the opposite direction of what you think. So if it says negative c, like -2, usually you think, okay, negative in my x directions, that would be to the left. But because it's a horizontal shift, I'm going to remember to go the opposite direction and move to the right. Horizontal moves opposite. Vertical does everything the way you would think. If you remember these, you save yourself a lot of work in terms of filling out a table. But if it's a test day and you blank, make a table. You will always be able to find the information that you need. You just have to make a table. In this case, I'm going to show you the pictures I have already drawn because I think they do a good job, and I will explain them. Because I did not make tables for any of these. Sorry, I'll leave that up there. It says we're going to graph the following all on one graph. We have an f of x function, which is x squared. That's our basic mother function. We have our g of x function, which is x squared minus 4. And then we have our h of x function, which is x minus 4 quantity squared. So for this g of x function, notice we have our x squared, and then we have the minus 4 at the end. Is this a vertical shift or a horizontal shift? It's a vertical shift because this negative 4 is outside of the x squared. And if it's a vertical shift, are we moving up or down? We're going to move down 4 units. Okay. So on my picture, the green one again is my basic mother function. One we've graphed every time. And then what I did was after I graphed that, I took each of my ordered pairs and I shifted them down 4 units. That's one of the reasons why I really like putting the mother function graph on first, because then there's really no math involved. I didn't have to make a table. I didn't plug anything in. I just simply dragged my 0, 0 point down until it was 0, negative 4. I drag it down my 1, 1, 1, 2, 3, 4, so that it's 1, negative 3. That's all I'm doing. Now, if you had to make a table, it would still work out that way. Because if I plug in the value into here for 1, 1 squared is 1, 1 minus 4 is negative 3. You still get the same outputs. So there's nothing wrong with doing a table. But if you do learn some of these basic translations, then it saves you some work. And if this would have said x squared plus 4, I would be taking all these points and shifting them up 4 units. That's how the verticals work. And so you can probably logically deduce that if the g of x function had a vertical shift, the h of x function has a horizontal shift. And hopefully we would be able to tell that anyways because we have the x minus 4 and then all of that is squared. So the minus 4 is happening inside the square, which means it's a horizontal movement. And since it's a minus 4, are we going to move to the left 4 units or are we going to move to the right 4 units? Yeah, correct. We're going to move to the right because it's going to go the opposite direction of what we think. And so what I did there is I started with my mother function and I took everything to the right, 4 units. But even if I didn't know that that's what that was telling me to do, I could still plug in 0. Plug in 0, and look what I'm going to get there. I'm going to have negative 4 squared, which is 16. That's going to be way up here. But that does match what's happening on my graph, because my red graph would keep coming up, 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 until it hits. So one thing with it is if you start getting a weird graph because you're doing a table, you might have to pick more x values. Because in this case, I would need to have my x values shifted over so I could get a better picture of what is happening. So if I did negative 2, 1, negative 1, 0, 1, and 2 for this one, I wouldn't even hit what I have graphed right now because I didn't go over far enough. And that's okay. But it's going to give you a weird looking graph to where it looks more like a line than a graph. And at that point, you need to think, okay, I need to probably pick some more points. Another reason why I strongly recommend knowing the difference between a vertical and a horizontal shift so that you're shifting things, sliding things over or down instead of actually plugging and chugging. On Pearson, they don't have you graph using the mother function, meaning they won't have you graph with the mother function and then move things around. That's what I do on paper because it helps me to see what actually happened and make sure that that lines up. If I know this is supposed to come down 4 units, but when I graph it like this, then hopefully that causes me to pause for a second and I can identify that I've messed up somewhere. Are there questions? Clarifications? All right. I'm going to scroll down. We've got to learn how to complete the square. Here's the other way you will see the quadratic function. So earlier we had it with ax squared plus bx plus c. This way is actually a little bit more user-friendly when it comes to graphing our quadratics. If you have a quadratic function that looks like a times comma, or parenthesis, the x minus h squared plus k, this way is actually nicely set up for you to go ahead and graph. Because from earlier we learned our vertex, which is either the highest point or the lowest point of our graph, is this hk. hk. And I told you we would get another form of our function and it would make more sense. This is that form. Regardless of which form of the function, though, your axis of symmetry is always the x equals the h. So that doesn't change. But this one actually gives you the vertex. And this looks a lot like the equation of a circle as well, if you remember the equation of a circle from any previous classes. So if we can get our quadratic function to look like this form, it's a little bit easier for us to graph. And I know for a fact Pearson has a lot of problems where you will be given the first form, the ax squared plus bx plus c. You'll be given that form, and they will ask you, what is the vertex of this quadratic? And unless you graph it, you have no idea, unless you can do completing the square. If we can complete the square on the ax squared plus bx plus c, we can get it into this format, and then we're able to identify the vertex and the axis of symmetry very easily without actually doing any graphing, just doing algebra. So some of you may have seen completing the square previously, again, maybe an Algebra 2 class or a college algebra class. I don't know if you would get to it in an Algebra 1 class. But when you complete the square, your main goal is to get a perfect square trinomial. And what that means is you are trying to get something, sorry, I'm covering that for just a second, so that you have an x plus or minus a number inside here that is squared. That is perfect square trinomial. This is what we're shooting for. Okay? So how are we going to do that? We're going to do that by adding 1/2 b squared to both sides and factoring. That doesn't have to make any sense to you just yet. We're going to do an example, and it's going to make more sense. A lot of times with math, you're given the information, but then actually seeing it played out is how you're going to learn to utilize it. And I will slide that up and keep that up there so you have the general steps while we actually work our problem. Because I looked through the notes, or I looked through the homework for this, and a lot of yours is asking for you to find the vertex of, let's see, do I have room over there? Yeah, I do. F of x equals x squared minus 4x plus 5. This is a quadratic function, but it is written in the form of ax squared plus bx plus c. That is not what we need. We need this to look like the f of x equals a times x minus b squared plus k. This is our goal. If we can rewrite the original function in this format, that's an H, not a B. Sorry. If we can write this in this format, the HK is my vertex, and I'm done. So this is where we're going to use completing the square. And for the purposes of doing the problem, I'm going to drop the function notation and change back to x's and y's. So instead of saying f of x equals x squared minus 4x plus 5, I'm going to go back to y. It just is a little bit more user-friendly as we work through the problem. So I'm going to go y equals x squared minus 4x plus 5. Now, remembering that this is, I'll write it over here, ax squared plus bx plus c. This is in that format. Okay? What is our b as it is written right now? Yes, our b is negative 4. It's good to note that early on. Okay? Now what I'm going to do is I'm going to move my constant to the other side. That's going to be my first step. So I'm going to subtract the 5 over. So I have y minus 5 equals x squared minus 4x. Oh, I should have left a spot over there. That's okay. And I'm going to put a plus blank, and then over here I'm also going to put a plus blank. And when I do it in my notes, I actually do draw in the plus blanks, because that reminds me that what I do to the right-hand side of my equation, I have to do to the left. Because 9 times out of 10, when students do completing the square, if they mess it up, it's because they will add over here and they won't add over here. And the only reason we're able to even complete the square is because by doing this, we're actually adding nothing. We're just like re-divvying up stuff. So what goes in this square? Or what goes in this blank is the 1/2 b squared. Up here it says, how do we complete the square? By adding 1/2 b squared to both sides. Well, you just told me my b is negative 4. So 1/2 b would be negative 2. So 1/2 b squared would be what? Positive 4. So I'm going to add positive 4 to both sides. And I will always do this part as well. Yes, I could do that in my head, but then if I mess up somewhere, I have nothing to go back and reference to figure out what I messed up on, if I drop a negative or something like that. So if I do this, it helps keep me in check. So why does this work? Well, x squared minus 4x plus 4. We have to factor this. And if you're not good with factoring, this will be where you get good at factoring. Factoring is where we split into 2 binomials like this. And we look at this first term, our x squared, and that tells us what is first inside of our binomials. So what times what will give me x squared? X times x. That's exactly right. And so the first term inside of our parentheses is going to be x. And then here's a neat trick. If this is positive, right here in front of our c, then that means the signs in here have to be the same. They're either both positive or both negative. And the way that we know what they are is we look in front of our b. This is a minus. So we have to have a minus in here. If this would have been a plus 4, then we would have had positive. Now, to find my last term inside of here, I have to know what times what will give me 4. 2 and 2. There's also 1 and 4, right? Let's just be real. 1 and 4 is also an option. But here's the deal. Here's what happens over here on the side if I do a minus 1 and a minus 4. I'm doing it small because it's not going to work. When I FOIL to check, I do my first, that gives me x squared. I do my outer, which gives me my negative 4x. Hey, that's good. But then when I do my inner, I get another minus 1x. That would give me a negative 5x. It doesn't work. So I know this set of factors does not work. 2 and 2, though, if I check it using FOIL, if I do my outer, I get a minus 2x, and my inner, I get a minus 2x. That's going to give me my minus 4x. And this is what we want to see. Because remember, the whole goal of completing the square is a perfect square trinomial. This is what we want to have happen. And if we've completed this square correctly, it will always happen like this, where what's in this set of parentheses will be exactly what's in this set of parentheses. Okay, popping over to this left side real quick, we have 4 minus 5, so that would be y minus 1. And I can write this as an x minus 2 squared. Oh, we're getting closer. Remember, we're trying to get to a times x minus h squared plus k. So let me add the 1 over. This is in the formatting that we wanted. Oh, thank you. What's on my screen on the computer is different than what's on your screen up there, which is different than what's down here. So thank you. Always let me know if you can't see something. So if we can get to this formatting, which looks like what we needed, who can tell me what my vertex is? So close. Just 2, 1. So notice the original format has a minus here. So if this is a minus here, then the h is just whatever this value is. We don't have to worry about the sign. So the vertex is actually 2, 1. So if you like writing out steps for completing the square, here's what you're going to do. You're going to subtract or add your constant to the other side. That way you only have your x squared and your x term. Put plus blanks on both sides. In those blanks, you're going to put 1/2 b squared. And on the side, I always make a nice little table of what my b equals, what my 1/2 b equals, and what my 1/2 b squared equals. Then you factor. Do you want to know something that's kind of neat about helping you to factor? Is if you do this table over here, do you notice anything that's similar between this table and what we factored? Yeah. 1/2 b was -2. We have x in our 1/2 b. That always happens. If you complete the square correctly, these always match. So you actually don't have to learn to factor all that much if you make the table. What I do always recommend, kind of like I did over here, is either mentally or on the side, FOIL what you have factored and make sure it actually goes back up here. Make sure you didn't drop a negative or add a negative somewhere. That's super simple to do. I've done it all the time, and students do it all the time too. Doesn't matter how many years you've done math, dropping a negative is another number one mistake. It happens. But if you FOIL this, that's a good way to check just to make sure. After that, you combine it by putting a square, and you add or subtract your constant back over so that you are in the correct format. Then you are ready to identify your vertex. So that is one way of identifying your vertex. And I have a feeling after I show you the next way, many of you will not choose to do it that way. That does not mean you shouldn't know how to complete the square, because remember, the midterm and the final are paper pencil. And if I ask you to complete the square and you use this new method I'm going to teach you, you won't get the credit. Okay? So know how to complete the square. This next method is easier and is a great way to check to make sure you got the right one. But the next one does require you to memorize a formula, or at least write it down somewhere. So here's how you find a vertex another way. Beep. Vertex formula. For f of x equals ax squared plus bx plus c, again, where a does not equal 0, the vertex is negative b over 2a, and then f of negative a, or negative b over 2a. If you know what your b's and your a's are from your general form, you can find the vertex. No completing the squared necessary. You still have to do some algebra. I'm not saying you get out of doing any algebra. But if you are forced to do completing the square, this is another safe way to kind of check to make sure your answer is actually correct.
Where does the A doesn't equal 0 come from?
From the very first definition of our quadratic function. Because if a equals 0, we lose our x squared term, and then we have a line. We no longer have a parabola. So we cannot let a equal 0. Any of the other numbers can be 0, except a. If a is 0, we no longer have a quadratic. So this example is going to specifically state, use the vertex formula to find the vertex of f of x equals x squared minus x minus 6. Now, if it didn't say use the vertex formula, you could do completing the square with this to figure out the other form and find your vertex that way. This one does specifically say use the vertex formula, and in the vertex formula, I need to know my A and my B. So the first thing I'm going to do is I'm going to identify what my A, my B, and my C are, just simply because it feels weird to find two of them and not the third one. So on the side, I will make A equals, B equals, and C equals. What does A equal in this function? It's 1. Good call. There is no number actually written in front of our x squared term. So when there's no number written there, it's 1. Because 1 times anything doesn't change it. So A is 1. What is B? Negative 1. Same concept. And C in this case is negative 6. Now we don't actually need the C, but like I said, I'm a little OCD and I still want to find it. So to find my x value or my h value for my vertex, I have to find negative b over 2a. Well, this is where we have to be careful. The original formula has a negative. So I'm going to have negative times whatever my b is. So b is negative 1 all over 2 times my a. Negative times negative gives you a positive. 2 times 1 gives you 2. So my vertex is going to be in the form hk. So I just found that the first part is 1/2. Halfway there. Unfortunately, that's the easiest part. The other part's not hard, but you do have to do algebra. More algebra than what we just did. So if you look here in the formula, we have f of negative b over 2a. What this means is we have to find f of 1/2. Because we just found that the negative b over 2a is 1/2. So we have to find f of 1/2, which means we have to plug 1/2 into our function everywhere there's an x, and we have to simplify. So I have 1/2 squared instead of x squared. I have minus 1/2 instead of minus x, and then I have minus 6. Fractions are going to come up in this class. If you're not totally comfortable with them, go to my YouTube site, go to my beginning algebra playlist, and go to 1.3. Nice long lecture on fractions. So this is saying 1/2 times 1/2 minus 1/2. How do I turn a whole number into a fraction? Put that thing over 1. That's exactly right. All whole numbers can be written as fractions if you stick them over 1. What's the rule when multiplying fractions together? Nope. Can't cross multiply. That's when you have a fraction equal to a fraction. But when we have a fraction next to a fraction, what do we do? That's right. We multiply straight across. So we multiply straight across the top. 1 times 1 is 1. We multiply straight across the bottom. 2 times 2 is 4. Now, we have a long subtraction problem here. We have 1/4 minus 1/2 minus 6 over 1. What's the rule whenever we do subtraction or addition with fractions? We've got to get a common denominator. Got to get a common denominator. So, if I look at my denominators, I have a 4, a 2, and a 1. Well, I can change 2 into 4. I can change 1 into 4. So I'm going to have 4 as my common denominator, which means I don't have to change my 1/4 at all. It can stay. In order to get a 4 on the bottom for my 1/2, what do I have to multiply 2 by to get to 4? 2. But if you multiply the bottom by 2, you have to multiply the top by 2. Because 2 divided by 2 is what? 1. Multiplying by 1 doesn't change anything. What we're essentially doing when we are changing the denominators like this is think about a pizza. You have a pizza that's cut in half, but then you need to make smaller slices. The amount of pizza you have doesn't change. You're just slicing it into smaller pieces. That's all we're doing by getting a common denominator. We're making smaller slices. And then how do I turn a 1 into a 4 using multiplication? Multiply it by 4, and if I multiply the bottom by 4, I got to multiply the top by 4. So you get 1/4 minus 2 times 1 is 2, 2 times 2 is 4, minus 6 times 4 is 24 over 4. Sorry. 1 take away 2 would give me a negative 1/4 minus 24/4, which gives me a negative 25/4. I will tell you, if they ask you to use the vertex formula, odds are you're going to get a fraction or some sort of a weird number. I wouldn't want to factor for this. I wouldn't want to factor to where I get negative 25 over 4. So my vertex then is 1/2 negative 25 over 4. I also wouldn't want to try and graph having that be my vertex. That would be really gross. But we could find this information either by completing the square or by using this vertex formula. Both of them would produce the exact same solution. Are there questions, clarifications? Okay. So what if you were asked to graph a quadratic function? And it's given to you in the form of ax squared plus bx plus c. What would you do? Well, these are the steps I would take. First thing, you don't even have to do any algebra. You just look at the equation. If your a is greater than 0, so if your a is positive, your parabola opens up. If your a is negative or less than 0, your parabola opens down. Then I would find the vertex. You can do that one of two ways. You can either complete the square or use that formula we just did. Either one. But finding the vertex will help you to know where your axis of symmetry is and know where to kind of start with your graph. Then I would find my y-intercept. That's where we plug 0 in for our x, which in this case is really nice because look, if we plug 0 in for our x, this term goes away, this term goes away, and we're left with just whatever our constant term is out here. That will always be our y-intercept. But that gives us another point to plot. Then I would find if you have any x-intercepts. You may or may not. The way you find that is you set your function equal to 0, and you're going to have to factor and solve. Step number 4 really helps solidify the factoring skills. After that, you have lots of information. You have a point for your vertex, you have a point for your y-intercept, and you may have up to 2 points for your x-intercepts. So you have lots of pieces that you can graph with. And we're going to graph, actually, the one we just found the vertex for. So some of our work is already going to be done for us. We're going to graph the x squared minus x minus 6. Step 1, does our graph open up or down? What is our A value? A is 1. Is 1 greater than or less than 0? Greater than 0, which tells us that we have a parabola that opens up. Step 2 is finding the vertex. We literally just did this one. Our vertex that we found was 1/2 negative 25/4. Again, not a pretty vertex, but it's a vertex. It gives us a point. On Pearson, you will never have to graph a point like that, so don't freak out that you're going to have to do that. And I'm not made enough that I would actually make you graph one like that on a test. Your numbers would be like 1 and 2, 2 and 3. But we've already done some of the work on this one, which is why we're going to keep going with this one. So step 3 is find the y-intercept. I need to find f of 0. Well, if I plug in 0 for x's, I just get negative 6. Be careful here because people get really, really relaxed that it's 0 squared minus 0 minus 6, and they'll put that it's a positive 6 because they'll forget that negative right there. So when x is 0, y is negative 6. Just kind of making notes so I have things to graph with. So we've already done steps 1, 2, and 3. Step 4 is where we set our quadratic equal to 0. So instead of saying f of x equals, I'm going to say 0 equals x squared minus x minus 6. And this is where we would solve. There's lots of different ways you can solve a quadratic function. The number one way that I always recommend for students to try is factoring. If you're not comfortable with factoring, get comfortable with factoring. Yes, there is the quadratic formula. You are more than welcome to use that if you are comfortable with that. There's songs for that. It Goes to Pops Goes the Weasel is the version that I know. You are more than welcome to use that. But I do find that if students rely on the quadratic formula, more often than not, they will drop a negative and it messes up their answer. If you learn how to factor, you're more safe. Because factoring is the opposite of foiling, and so you can always check your answer by foiling. Foiling is the first, outer, inner, last. So factoring, we just did this on our completing the square problem. Again, I have an x squared, so I know my first term will be an x and an x. Notice the sign in front of my c is negative. If it is negative, then I will have a plus and a minus. Always. If this one is negative, I'm going to have a plus and a minus. Now, I need to think of what times what will give me 6. There's 1 times 6 and 2 times 3. So here's what I need to have happen. I'm going to put a 1 and a 6 or a 2 and a 3 in these spots, but then when I add them together, I need to get to a negative x. Well, if I put a 1 here and a 6 here, that's going to give me a negative 5. If I put the 6 here and the 1 here, that'll give me a positive 5. This one's not going to work. So it's going to be 2 and 3. Since I need to end up with a negative x, that means I need to have more negatives than positives. So I'm going to put the 3 over here, and I'm going to put the 2 over here. And we can always check our factoring by foiling. If I do first, I get x squared. If I do outer, I get negative 3x. Inner, I get positive 2x, which does give me a negative x overall. Last is a positive 2 times a negative 3, which gives me a negative 6. I have factored this correctly. And the whole reason why we want to factor is now I have something times something equals 0. This is known as our zero product principle. You don't have to know that. But when you get it factored, what you do with this is you take each of your factors and you set them equal to 0. And you solve. X plus 2 equals 0. I would subtract the 2 so that x is negative 2. X minus 3 equals 0. I would add 3 to both sides. So x equals a positive 3. So what I just found were my x-intercepts. I found that negative 2, 0 is on my graph, and I found that 3, 0 is on my graph. I have lots of ordered pairs now to graph with. And I'm going to cheat a little bit just because the graph that I have on my paper is going to be a lot nicer than the one I throw up here in just a second. So I've done all the steps. Step number 5 is graph. I know I have to have an upward facing parabola. I know the vertex, or the lowest point of this, happens at 1/2 negative 25 force. I have a y-intercept and 2 x-intercepts. Those are all the pieces that I have. And so I graph all those pieces. This is negative, actually it's not even a correct graph. Yes it is, except for that one. That should be shifted over. So this point is wrong. It should be over here at 3. But negative 2, I plot negative 2, 0. I plot negative, or 0, negative 6. My vertex, though, happens at 1/2, and then negative 25 force. And then I would actually connect all the way over here at 3, 0. It'd be a little bit fatter of a graph. I told you, even I make mistakes. It happens. So lots of steps to find the pieces, but not really any of the steps are super hard if you can factor, and if you either can complete the square to find the vertex, or you have your vertex formula to help you find that vertex.